Lesson 53 gave us a sigma algebra F, the referee that decides which subsets of omega are even allowed to count as events. But our referee doesn't tell you the score. Knowing a set is a legal event says nothing about how likely it is. We need one more piece. A probability measure, P, is a function from f to the interval 0 to 1, satisfying two rules on top of the sigma algebra we already have. First, P of omega equals 1. The whole sample space gets probability 1. Something happens, full stop. Second, countable additivity. If A1, A2, A3, and so on are pairwise disjoint events in F, then P of their union equals the sum of P of AI. Together, omega, F, and P form a probability space. This is exactly the definition of a measure from measure theory, with one restriction. A general measure mu sends f to 0 up to infinity and only needs countable additivity, no requirement that the total equals 1. Counting measure assigns every finite set its cardinality. Mu of A equals the number of elements in A, with no upper bound at all. Lebesgue measure assigns an interval its length. Mu of the interval A, B equals B minus A. Again, unbounded, and it's the rigorous footing under every integrate over x from calculus. A probability measure is simply a measure normalized, so the whole space has mass exactly 1. Every theorem measure theory proves for mu. Monotonicity, continuity, subadditivity transfers to P for free. Watch the familiar probability rules fall out as theorems, not separate assumptions. Monotonicity. If A is a subset of B, then P of A is at most P of B, straight from additivity applied to B as A union the leftover piece. The complement rule. P of A complement equals 1 minus P of A, since A and its complement are disjoint and together make up all of omega. And subadditivity. P of A union B is at most P of A plus P of B, with equality exactly when A and B are disjoint. The union bound used all over this course, now a one-line consequence of the axioms. A probability measure. A function P from f to 0, 1, with P of omega equal to 1 and countable additivity over disjoint events. Together with omega and f, it completes the probability space, omega, f, p. It's a measure in the full measure theoretic sense, just normalized to total mass 1. Every measure theorem about mu is a theorem about P. Next, Lebesgue integration, the machinery that turns expectation E of x into an integral of x against the measure, P itself.